a really mind-bending what if from the quantum world. We all learn about the electron, right, as a fundamental particle.
Hmm.
But what if it isn't? What if it's actually made up of even tinier things?
Hmm.
We're going to explore this idea, these hypothetical sub-electron particles, SEPs for short, and look at how this concept might, maybe, offer a surprisingly intuitive way to grasp some of the electron's weirdest behaviors. And hopefully you can follow along without needing that physics PhD.
Exactly. Look, this isn't about chucking out the textbooks tomorrow morning. It's more a thought experiment, really. Pushing the edges of how we think. Our sources explore this idea, this hypothetical substructure. Not a solid spec, but maybe a dynamic collection of things.
Right.
We'll see how this might map onto things like the electron cloud and that famous particle wave duality.
Okay.
But, and this is crucial, we also need to look really hard at the challenges, the big problems this idea runs into when you compare it to, well, everything we know that works.
Stacking it up against established physics.
Right. Think of it as, I don't know, a little peek behind the quantum curtain, maybe.
Okay, let's start there. With that kind of hazy picture we get of electrons around an atom, the electron cloud. It's not like a solid shell or anything like that.
No, definitely not. It's really just a probability map, a mathematical description of where you're likely to find the electron.
Okay. So how could these SEPs, these sub-electron particles, give us a better handle on that?
Well, the shift in thinking is this. Instead of one particle being sort of smeared out, which is hard to picture,
Yeah.
imagine the electron is actually made of countless tiny SEPs, all moving incredibly fast, constantly. Just the sheer number of them, always zipping around, would naturally form this diffuse, cloud-like region.
I see. So where there are more SEPs bunched up, that's where the probability of finding the electron is higher.
That's the core idea. The density of the SEP swarm at any point would correspond to the quantum mechanical probability. It's a bit like trying to pinpoint, say, a single gnat in a huge, fast-moving swarm.
Right. A super fast, super tiny swarm of gnats. The whole swarm looks blurry, but it's made of individuals. Okay, that kind of helps visualize it. So does this SEP idea also connect to the different energy levels an electron can have in an atom?
It could, hypothetically. You could imagine different energy levels corresponding to different stable arrangements, maybe different dynamic patterns within the subswarm. Perhaps higher energy means the swarm occupies a larger average volume, or the SEPs move in a different, more energetic, coordinated way.
Different modes of the swarm, maybe.
Exactly. Different stable configurations or resonances of this subparticle system. It offers a conceptual hook for those quantized energy states.
Okay, now for the part that honestly always makes my head spin a bit. Particle wave duality. How can this thing we picture as a tiny point particle also act like a wave, spreading out, interfering?
Yeah, it's one of the deepest quantum mysteries, isn't it? But again, the SEP model offers a different perspective. Maybe the wave-like behavior isn't fundamental to one thing, but emerges from the collective.
How would that work?
Think about the coordinated motion of all these SEPs. You could have density variations, like ripples, moving through the swarm. It's maybe analogous to sound waves in air. The wave isn't the air molecule itself, it's a pattern of compression and rarefaction of the molecules.
So these ripples in this SAP could act like waves.
Potentially. If these SAPs can move together in a coherent way, their collective behavior could produce interference and diffraction when they encounter obstacles, like the slits in the double slit experiment.
Ah, okay. So when an electron goes through two slits and makes that interference pattern, in this picture, it wouldn't be one electron wave interfering with itself, but the whole SEPI swarm interacting with the slits, and the pattern emerges from that collective action.
Precisely. The wave-like phenomena become an emergent property of the many components acting in concert, rather than an intrinsic property of a single entity.
Okay, that's one side. What about the particle side? When we actually detect an electron, it hits a screen at a single point, like a particle.
Right, so the SEP model needs to explain that too. The idea here could be that the act of measurement, the interaction with a detector, forces the SEPs to, well, coalesce.
Coalesce, like clump together.
Yeah, maybe the interaction disrupts whatever keeps them spread out, causing this normally diffuse swarm to temporarily collapse into a highly localized, compact state.
Like the gnat swarm suddenly condensing into one spot when you try to swat it?
Kinda, yeah. A temporary condensation triggered by the measurement. But crucially, where it condenses would still be probabilistic.
Ah, linked back to the density.
Exactly. Linked to the initial density distribution of the SEP swarm right before the detector interacted with it. More SEPs in a region means a higher chance of coalescing there.
Okay, I have to admit, conceptually, it's intriguing. It gives you a sort of mental playground for these really weird quantum ideas. But as you said right at the start, there've got to be some major problems with this, right? Huge hurdles.
Oh, absolutely. Immense ones. First off, the most obvious. We have absolutely zero experimental evidence for these SEPs. None. They'd represent a whole new layer of fundamental particles beyond the standard model.
And you'd need forces to hold them together.
Exactly. And not just any forces. You'd need entirely new fundamental forces, incredibly strong ones, to bind these SEPs into an electron so tightly that it looks fundamental. Think about how stable electrons are. These forces would have to be unbelievably powerful to prevent them from just flying apart. The energy involved would likely be enormous.
Way beyond things like the strong nuclear force holding quarks.
Potentially, yes. It really highlights how fundamental and stable the electron appears in all our experiments.
And what about the fact that every electron is identical, same charge, same mass, everywhere in the universe?
That's another massive challenge. How would a collection of SEPs always add up to the exact same total charge and mass?
Would each SEP need to carry a precise fraction, like exactly 1,000th of the electron charge or something?
It seems like it would have to, which just pushes the question of quantization down another level, doesn't it?
Yeah, it feels like you're just shifting the problem.
And then there's spin, the electron spin. That intrinsic quantum property, spin 12, it's not like a tiny ball actually spinning in the classical sense. Explaining how a collection of particles, these SEPs, would collectively produce that specific quantized spin 12 property is.
Oh, it's extremely difficult to conceptualize.
Right, it's not just like adding up little spinning tops.
Not at all. Classical analogies break down very quickly with quantum spin.
And experiments. You mentioned challenges there too. Haven't we smashed electrons really hard to see inside?
We have indeed. Experiments called deep inelastic scattering. They basically fire high-energy projectiles at electrons. It's like using incredibly tiny probes to see if there's any internal structure. And down to the smallest scales we can currently probe, something like 10 to the minus 18 meters, the electron still looks like a point. No size, no internal parts detected.
Wow. So any SEPs would have to be confined in an unbelievably tiny space and bound together with truly immense energy. Otherwise, these experiments would have ripped them apart and we'd have seen something.
Okay, so new particles, new forces, explaining charge, mass, spin, fitting inside that tiny space. What else? You mentioned QED earlier.
Ah, yes, quantum electrodynamics. This is maybe the biggest hurdle of all. QED is our theory of how light and matter interact, specifically electrons and photons. And it is staggeringly successful.
Oh, successful.
I mean, its predictions, like the magnetic moment of the electron, match experiments to an incredible number of decimal places. It's one of the most precisely tested theories in all of science.
Okay, so a big deal.
A huge deal. Any SEP model wouldn't just have to explain the cloud and duality in a nice visual way. It would have to perfectly reproduce every single successful prediction of QED under all normal conditions. The collective behavior of these hypothetical SEPs would need to be mathematically and experimentally indistinguishable from a fundamental QED electron in all the scenarios we've tested so far.
That sounds almost impossible. Like making a clockwork bird that perfectly mimics a real bird in every single way.
It's an extraordinarily tall order. And it leads to another kind of philosophical issue, too.
Which is?
Well, if electrons are made of SEPs, what are SEs made of?
Ah, the turtles.
Exactly. Turtles all the way down. Where does it stop? Are there sub-electron particles? It introduces this potential infinite regress.
Okay, my head is definitely spinning now.
And just practically speaking, think about the energy required to actually break an electron apart, assuming it could be broken. The binding energy holding those SEPs together would likely be far beyond anything we can currently generate.
So, impossible to test directly, maybe?
At least with current and likely near-future technology.
Which brings us back to simpler explanations. Occam's razor, right? The idea that the simplest theory that fits the facts is usually preferred.
Precisely. And right now, the standard models picture the electron as a fundamental, indivisible particle is vastly simpler than introducing a whole hidden zoo of SEPs and new forces with no direct evidence.
It fits all the data we have extraordinarily well.
It does, introducing this extra layer of complexity without any compelling experimental reason. It goes against that principle of parsimony. We should always be open to new ideas, of course, but the burden of proof here is immense.
So let's try and wrap up this deep dive into this hypothetical electron structure. It sounds like, while this SI idea is conceptually kind of neat, maybe helps visualize the electron cloud, maybe gives a different angle on particle wave duality, it just crashes headlong into some enormous problem.
That really sums it up.
Yeah.
It opens a Pandora's box of theoretical challenges,
Yeah.
new particles, new forces, explaining charge, mass, spin, consistency with QED.
And contradicts experimental evidence showing the electron is point-like.
Exactly.
Yeah.
So while it's a really valuable thought experiment, I think,
Mm.
it helps us appreciate just how weird quantum mechanics actually is and how solid our current theories like QED really are. But based on everything we know, the evidence overwhelmingly points to the electron being fundamental, at least for now.
Okay, so here's a final thought then, something for you to chew on. Given how solid the evidence is for the electron being fundamental, what kind of earth-shattering, completely unexpected experimental result do you think it would take? What would have to happen for physicists to genuinely start questioning the standard model on this? What kind of observation would make them sit up and say, whoa, hold on, maybe there is something inside after all? Makes you really think about the limits of what we know and what the future might hold, doesn't it?